Hello, everyone. Thank you so much for attending today's workshop. Today, we're going to talk about Stumpy, a powerful tool for modern time series analysis. My name is Nima, and I am one of the contributors of this library. Okay, so if you have any questions, feel free to ask your questions in Zoom, or for those who are here right now, you can hold your questions, and we're going to answer them at the end. Okay, so let's say you want to use a tool, right? There are two things that you need to know. One, how to use the tool, but more importantly, what the tool does, right? Because you need to understand what the tool tries to solve for you before even jumping to use the tool. So now let's say you are this detective with this cool magnifier, and you want to find something. Okay, so let me give you this data, this time series with 1,000 data points. And I ask you, find something for me. Find something interesting. Or can you get some insight from this data? Or extract some information from this time series? Well, visually speaking, you can see that it's not possible to get something out of this time series. So let's make things simpler. So I'm going to give you this time series with only 10 data points. And I ask you, what do you see here? Well, maybe you look at the maximum, or maybe you want to look at the minimum. Maybe you want to take the average of the whole data or standard deviation. But all of these are like global summary statistics. So while they are informative, they are barely useful because they are not giving you a good amount of information, right? So if, for example, you have two maximum, the surrounding data points for those maximum points might be different. So for example, one of those maximum values, let's say is 1,000, right? And the surrounding data points might be 0, 0, 0, 1,000, and then 0, 0, 0. But for example, for the other maximum in your data, it might be 1,000, 1,000, 1,000, and 1,000, 1,000, 1,000. So it's like a constant, right? So what I'm trying to say here is that the context matters. So what we're going to do is that we're going to consider like a window, right? To consider the context around the data points. And this is what I call subsequence, which is a continuous part of a time series, right? So this is, for example, here I'm showing a subsequence of length 3. Now, we are trying to use these subsequences to analyze this time series data. So let's look at this time series. I'm going to consider this red window, right? This is like a subsequence with length 2, right? For the sake of simplicity, I'm just considering like a length 2 for the subsequence. So I'm using x1 and y1 to represent the first data point and the second data point of this subsequence. And what I can do right now is that I can map this subsequence to a R2 space with the coordinate x1 and y1, right? And if I consider like another subsequence with x2 and y2, I can represent it as a single data point in an R2 space as like with the coordinate x2 and y2. Now, if I ask you, how do you compare these two subsequences? Well, the intuitive way is just to look at like the distance between these two data points in the R2 space, right? Which is like a Euclidean distance. So in this case, for example, it is 0.55. Now, what if, for example, you have a subsequence of length 3? Then we are going to map them in the R3, right? Or three-dimensional space. But if you have a subsequence of length 4, we're going to map them to the four-dimensional space. But the concept is the same. Now, we are going to apply this concept to all subsequences in this data. So on the left, I'm showing the time series. In the middle, I'm representing those subsequences as single data point in the R2 space for subsequences with length 2, right? And on the right, I'm showing the distance matrix, which basically contains the pairwise distances between those data points in the middle figure. So let's fix that red subsequence on the left, which is shown as a red single data point in our R2 space. And we are going to compute its distance to the blue window, to the blue subsequence. And we write that distance in distance matrix. So you can see that the second row basically like represent the distance between that red subsequence and the blue subsequences that as I move from left to right. So as I move from left to right, I compute the pairwise distances, and then I put them in the second row of this distance matrix. And I can do it for all other subsequences as well. So by doing that, I can fill in that distance matrix. So now we are at a good position to define matrix profile. So we start with subsequences of our data. We compute this distance matrix. And now what is that? That is the distance between the first subsequence and its first nearest neighbor, or the first nearest neighbor, or the closest subsequences among other subsequences. So if I go, for example, for the second row, there's basically the distance between the second subsequence and its first nearest neighbor. And I can do that for all other subsequences. So basically, I'm going to find the lowest value per row, and then I put them together, and I create a vector. And this is what we call matrix profile, which basically shows the distance between each subsequence and its closest subsequence. Now, if I have that, now you can get many things for free. You can get motifs. So motifs, when you have when you have like the two closest pattern. So for example, if you have this data, and if I ask you, okay, can you tell me the two closest pattern here? Well, it might be hard, right, to just visually just look at the data. So let me give you the matrix profile. So let's say you magically get this matrix profile. Now, if I ask you the same question, right? What are the two closest patterns here? Well, one of them is here, the global minimum of the matrix profile, which shows the start index of the subsequence, right? Shown in the in red. Now, if I zoom in, I can plot that here. Now, I said that there are the closest pattern to this one, right? So there are two patterns, right? The other one, well, it is the other global minimum in the matrix profile, and it has the and shows the start index of the blue window, right? The blue subsequence. And if I zoom in, I can plot it here, and you can see they are very close, right? But not only motifs, but you can also find discords. So discords are like potential anomalies. So a subsequence that is different than other subsequences in your data, right? Something that stands out to you. So if I look at the same data again, and if I ask you, what is the strange subsequence here? And remember that for the motifs, we look at the global minima. Well, here we look at the global maxima. And if I plot that subsequence that's shown in red, and I zoom in, and you will see that the pattern is like this, right? And if I try to find the best match to this pattern in that data, that will be this blue one. So among all other subsequences, the best match to the red one is the blue one, and you can see that they are still far away in this sense. Now, in addition to the motif and discords, you can find snippets, which means that if you have a time series data and you want to pick 2 or 3 subsequences that can represent the behavior in your data, you can also find chains, which are a series of subsequences that are evolving throughout time. You can find or detect emerging behavior. So let's say you are working on like a sensor data, and you're trying to, for example, understand like its behavior, right? And maybe you detect some behavior, and you might think, okay, so that can be an anomaly. So let's monitor it. And then you will see that, okay, so that occurs again and again. So that is like an emerging behavior in the system. You can use it for machine learning classification. So if you have, for example, two sum series data or a bunch of sum series data, and you want like to put them in class 1 or 2 or 0 or 1, you can use matrix profile and much more. So I encourage you to go to the Stumpy documentation and the tutorials. I provide the link at the end of this presentation. And also, if you don't understand something or you have some questions, you can ask your questions on the discussion in the GitHub repo, and I'm going to provide the link for that as well at the end. Okay, but everything seems to be good, right? But there should be a catch, right? So something might not be right here. So let me revisit the process. So we start with a time series with n data points and a subsequence of length m. We showed that the subsequences can be represented with data points in an RM space. We computed the pairwise distances and put them in distance matrix, right? And then from there, we computed matrix profile. Well, if we go with this naive approach, the time complexity and the space complexity will be n squared m and n squared. And it's not going to work if you go beyond 10,000. Yes, if you have like a short time series, you can go with a naive approach, right? But if your time series has 10,000 or more data points, that's not going to work, and the problem can become intractable. So in 2016, a PhD student, Michael Ye, and two professors, Iman Ko from University of California, Riverside, and Abdullah Moin from University of New Mexico, started working on a paper called Matrix Profile. And they showed that they can reduce this to On squared and On. Now, instead of, for example, storing the whole distance matrix and compute the matrix profile, they are just storing like the vector and they keep updating that, right? So that the space complexity can become On. And the time complexity now is independent of the length of the subsequence. Now, after that, they started publishing other papers back to back, like to each other, and published like matrix profile 1, 2, 3, and then you can like check their website on matrix profile. So there are like, I don't know, like 20 plus papers on matrix profile. And then in 2019, Sean, who was working on this matrix profile and implementing that in Python, released the library Stumpy as open source software. Then in 2021, I found the software while I was doing my research in my PhD, and then I found it cool. Yeah, okay, so let's contribute to this project. So I started working on several things in this library, such as tutorials, performance, code stability. We now have top K matrix profile. So instead of just the first nearest neighbor, you can go for up to kth nearest neighbor, and also the precision in numeric calculations. And in 2023, we have a Stumpy version 1.12. Okay, so a Stumpy at its core is on Python, of course, right? We are using 3 libraries in Python. So one of them is NumPy, which is for numeric computation. The other one is SciPy for scientific computation. And in addition to these two, we are using a Numba, which is a package that you can use to boost the performance because it has like a JIT-compiled function. So you can use like a JIT decorator to speed up like the computation. It also allows you to use the threads in your core to run your job in parallel. It also supports CUDA, which is like a platform that you can use to run your program on GPU. So these are the main dependencies in Stumpy. So in Stumpy, we have comprehensive unit testing. So we usually start with something that we call TDD, or test-driven development. So we start with adding unit tests, and sometimes like we go with the naive approach to create like another function, and then we start with the performance version. We also have 100% code coverage, where you may say, okay, 100% might be an exaggeration, but I can say that we tried our best to make sure that the code is very reliable. In fact, this started, I think, as I said, 2019, and it has been 4 years, and we maintained the code coverage, like 100% code coverage since then. It is tested on major platforms, Windows, Mac OS, Linux. It supports Python 3. It supports parallel computing. So if you want like to run your program on, let's say, multiple like GPUs or like servers in your core, supports that. It supports distributed computing. So if you want like to have like multiple servers and you want like to program on the servers, you can use that. It supports top key matrix profile. It has a well-designed code base. So it not only have a user-friendly public API that you can go and work on it, you can also take advantage of its cool private API. And you can take those pieces and put them together and build what you want. So recently there was a paper in matrix profile called the Discord Ever Matrix Profile, or DAM, for anomaly detection. And I was able to implement like the first version of it in 2 days. Of course, there are a lot of things that needs to be done, but what I'm saying is that it is very easy to prototype your product with the Stumpy. It supports the normalized Euclidean distance. So remember that I showed you that you can represent the point in the 2D space and compute the distance, Euclidean distance. But it also supports the normalized Euclidean distance, which basically you z-normalize or standardize your subsequence first, and then compute the distance. So this is useful when you are you want to consider like the shape rather than the magnitude. So it basically considers the correlation between those subsequences. And this is actually the default distance that is used in the original matrix profile paper. It also supports Minkowski distance. So the Euclidean distance that I mentioned in the R2 space, that is just a special case in the Minkowski distance. Okay, so remember that I showed you this time series data and the matrix profile, and I told you that, let's say you magically have it. Well, in fact, you can magically have it, like almost magically. And it is very simple in Stumpy. So it's just one line of code. Well, I mean, 2 lines if you want to consider the import part, but you just pass in like your data T and your length of subsequence M as, I don't know, like 600, for example, and it returns the matrix profile, and that's it, right? And let's say you want to run it on multiple servers, right? You can do it with just adding 2 characters at the end of that function, like a stump, and that's it, right? And you can have like some int, and then you run it, and then it will give you the data. If you have a CUDA enabled GPU and you want to run it on the GPU, you just add 4 characters, like GPU underscore stump, and that's it, right? And then you can run it and just get the result. Again, the cool thing here is that all of these are, like most of it, are functional and modular. So that's why it's easy to work with it and then put this together, put the pieces together to get what you want. I told you all about this. So I mean, we can, of course, go deeper as we want, but I think we should stop at some point. So I think you should go to the documentation. I provide like the link here to read more. There are a lot of tutorials out there on this document on this link. Go through the tutorials, try it yourself. If you don't understand it, just feel free to ask your questions on the GitHub discussion, which is the 3rd link here. And if you want to just explore the Stumpy itself, like the code base, and make yourself familiar like with the design and the structure of this library, I provide like the link to it as well. It's like the 2nd link here, the GitHub repo. This is me, and this is my GitHub, my LinkedIn, and my Twitter. If you want like to look me up. And this is the cool creator of this package, Sean. This is his GitHub, his LinkedIn, and his Twitter as well. So feel free to have a chat with him. He's a very nice guy. I can tell you that. And that's it. I don't know how long